Till now, we've been discussing the prospective or the observational approach, where there is a significant amount of professional judgment brought to bear on the creation of similar exposure groups or SEGs. In this next section, we are going to study what is known as the sampling approach. And here, we don't depend on the professional judgment of the exposure assessor or industrial hygienist at all. In this approach, the entire population of workers, irrespective of the task or job they're doing, is randomly sampled. And only after that, and only on the basis of the measurements, are they subsequently divided into similar groups. This requires multiple measurements of every sampled worker so that we can estimate the between and within worker components of variance. Let's discuss this approach a little bit more in depth and quantitatively. We are going to develop a one-way random effects model to determine the between and within worker components of variability. Let us assume that there are K workers who have been selected for sampling within this population of workers. And for the ith worker, let us assume that there are n sub I measurements. So each worker is being sampled multiple times, and for the ith worker, there are n sub I measurements. And thus, the total number of measurements made for this similar exposure group is given by capital N, which is the summation of the n's of I for all the workers. Now let us take the log transformation of each one of these measurements. And so Yij would be the log transformed exposure of the ith worker on the jth day. And so now we can express this log transformed exposure, Yij, as the sum of three terms. There is a mu, which is the mean exposure of the entire group of workers. And we are talking about the arithmetic mean of the log transformed measurements. The B sub I is the random deviation of the ith worker's mean exposure from the mean exposure of the entire group. And then the third term, Wij, is the random deviation of the exposure of the ith worker around that worker's mean exposure, mu's of I. So we can see that we start off with an overall global mean for all the workers, and that is mu. And then we say, how does each worker's mean exposure deviate from that mean? So that's the term b's of I. And then we say for each worker, we have multiple measurements, and how do each of those measurements vary from that worker's average exposure, b's of I. So there are between worker exposures denoted by b's of I, and then the within worker exposures that are within worker variations. So there is a global mean for all the workers denoted by mu, and there are variations of each worker's mean exposure from that mu, and these are denoted by b's of I. And then for each worker, there are multiple measurements, and these measurements deviate and vary around that mean value, and these are denoted by Wij. Thus, b's of I refers to the between worker variability, and it is normally distributed with a mean of 0 and a standard deviation of sigma sub b, and this is the between worker standard deviation. Wij refers to the within worker variability, and it is normally distributed too, with a mean of 0 and a standard deviation of sigma sub w. And the two components of variability are independent, and the total variance sigma t squared is given as the sum of the sigma w squared and sigma b squared. So the sum of the within worker variance and the between worker variance adds up to the total variance. Now, the exposure distribution of the ith worker has a mean value that is given by mu sub xi, and so these are in the non-log transformed form. So mu of xi, which is the mean of the exposure distribution of the ith worker, is given by the exponent of mu of I plus 1/2 of sigma w squared. And the mu of I and the sigma w squared are the mean and the standard deviation of the log transformed values of the ith worker. The between worker distribution, that is the distribution of the means of individual workers, mu's of I, has a mean of mu, this is the global mean that we discussed in the previous slide, and a variance sigma b squared, which is the standard deviation of the between worker variability. Also, the log of mu xi is normally distributed with a mean of the exponent of mu, which is the global mean, plus 1/2 sigma w squared, which is the within worker variance. And the log of mu's of xi has a variance of sigma b squared, where sigma b is the between worker variability. And the geometric standard deviation of the within worker variability is given by the exponent of sigma w, and the geometric standard deviation of the between worker variability is given by the exponent of sigma b. Using this framework, two researchers, Hans Kramhout and Steve Rappaport, challenged the observational approach. And they analyzed a large number of worker groups, what were considered to be SEGs, 183 of them, and these were obtained from 45 different studies reported in the peer-reviewed literature that had a minimum of at least 2 personal measurements per worker in each group. And the analysis of variance, or ANOVA model described above, was used to determine the between worker and within worker components of variance in each group. And they found that roughly 80% of the groups had workers who were not similarly exposed. And the variation between workers in an SEG, and they expressed this as the ratio of the 97.5th percentile to the 2.5th percentile. And they call this quantity as R, 95. And so the variation, the R value varied between 1 and 2,000. So that is a tremendous amount of variation in one similarly exposed group of workers. And their conclusion was that the observational approach can sometimes lead to excessively high variability within an SEG, so that some workers at the tail of the distribution may face much higher risks. In other words, some of the workers' exposures may be misclassified, and those workers should not have been placed in this group. Maybe they should have been in a group by themselves or in a different group. The idea is this: if the within worker variability is the dominant source of variability, then the exposure is being driven by process variables and ventilation that affect all workers to approximately the same extent. And if the individual workers have exposures that are significantly different, then those differences most likely arise due to differences in individual tasks and work practices, and not differences in the environment. And an observational classification approach may not be able to detect these differences between workers, and thus lead to misclassification. An observational approach can only detect changes in the environment, and it is not very good at looking at differences between workers, two workers who are doing the same job, but doing it differently enough that there is a large variation in the exposures cannot be efficiently and effectively detected by the observational approach. So instead, Rappaport proposed a retrospective classification scheme as opposed to the prospective observational scheme. And here, the entire population of workers is randomly sampled and subsequently divided into groups such that the R95 for each group does not exceed 2. In other words, that the between worker geometric standard deviation is less than 1.2. And such groups are called as monomorphic groups. And as we can expect, this approach requires multiple measurements of the sampled workers' exposures to estimate both the between and within worker components of variation. Since the classification of workers is done after sampling, this approach is commonly referred to as the sampling approach to classification.